Epilepsy is a disease characterized by seizures. Epilepsy, there are different types. There's seizures that are well localized in the brain or that spread out throughout the whole brain. In this video, we're only going to focus on the pharmacology of epilepsy. So here I'm drawing the brain, and the brain is made up of cells known as neurons. In epilepsy, you have episodic high-frequency discharge of impulses by a group of neurons in the brain. It can be in one part of the brain, so localized. This will create what's known as a partial seizure, or it can start local and then spread throughout the brain or throughout part of the brain, and this is known as generalized seizure. Now, before we go into the pharmacology of epilepsy, I think it's important to watch a video on how the neurons send signals to one another, and I have a video on that which I'll provide the link. So again, epilepsy is characterized by seizures, and it's where the neurons are excited. They just send all these impulses all the time. So therefore, drugs to treat epilepsy can be divided into three types. 1. Drugs that modulate voltage-gated ion channels responsible for the propagation of the impulse. 2. Drugs that enhance basically synaptic inhibition, so stopping the impulses. Or 3. Drugs that stop or inhibit synaptic excitement. So drugs that modulate voltage-gated ion channels are drugs that target the sodium and calcium channels, and they will inhibit these channels. Drugs that enhance synaptic inhibition will cause increase in GABA activity, which is the inhibitory neurotransmitter in the CNS. And then drugs that want to inhibit synaptic excitement will essentially decrease glutamate activity. So again, to recap, in the central nervous system, you have two main neurotransmitters that sort of counteract one another. These are glutamate, which are excitatory neurotransmitters, and then you have GABA, which are inhibitory neurotransmitters. So this cell here, let's just say, is a glutaminergic neuron, and they will, excite the brain. They will send impulses and stuff like that, and of course it will stimulate this postsynaptic neuron, and this, if this happens, it will result. If it hits a threshold, it will result in a seizure. And then you have this other neuron here in blue, which is an inhibitory neuron, and these inhibitory neurons release GABA. GABA, again, is an inhibitory neurotransmitter. And again, this neuron that releases glutamate is an excitatory neuron. So let's zoom in here where all these synapses are occurring and then learn a bit more about the physiology and then the pharmacology. So here I'm drawing the glutaminergic neuron, the terminal bulb, and then here we have the postsynaptic neuron, and then the blue here is the GABAergic neuron. So when an action potential comes down again, it essentially causes an influx of sodium via the voltage-gated sodium channels. And then once it hits the terminal, this will cause the voltage calcium channels to open up, resulting in calcium to come in, and this will then lead to depolarization, more positive, resulting in the vesicles in the terminal bulb to release glutamate in this case. Glutamate will bind onto receptors or channels in the postsynaptic neuron. In this case, the glutamate neurotransmitters are binding onto the AMPA and NMDA channels, resulting in the influx of sodium and calcium from outside, which will then lead to depolarization, reaching a threshold, which will result in an action potential. So this is creating impulses, it's stimulating the neurons in the area. And if this happens like a lot or consecutively, this will result in what's known as a seizure. So I hope that part of the story made sense and how that's like exciting, the neurons are exciting each other. And then here in blue, we have the GABAergic neuron with GABA in the terminal bulb. GABA is actually made from glutamate. But anyway, this neuron can release GABA, right? And the GABA can then bind onto its own receptors on the postsynaptic neuron here, which are, in this case, GABA-A receptors. When GABA binds onto this receptor, it will actually cause an influx of chloride ions, which are negatively charged, and so it sort of counteracts the depolarization, so it inhibits this process from happening. Once GABA, finishes its job, it gets taken back up to this terminal bulb, and then it gets converted to SSA through GABA transaminase. So that was sort of, so as you can see, we have, glutamate neurotransmitters, which, are exciting the cells, and then you have GABAergic neurons, which releases GABA, and GABA are the ones that inhibit, sort of suppress neuronal activity. So this is regulated normally, but again, in epilepsy, you have more excitement. So now let's talk about the pharmacology, the drugs used to treat epilepsy. Let's begin with the drugs that modulate voltage-gated ion channels. And these drugs include carbamazepine. Side effects here in the sad face include water retention, sedation, ataxia, and mental disturbances. Phenytoin is another drug, and side effects include confusion, gum hyperplasia, skin rash, anemia, and it's also teratogenic, so it's not good for pregnancy. You have ethosuximide. Side effects include nausea and anorexia. And finally, in this group, we have lamotrigine. Then you have the other class of antiepileptics that want to stimulate GABA activity. And these drugs include benzodiazepines, V-gabatrin, and tiagabine. I hope I pronounced those right. So if we were to draw those drugs up in respect to this diagram, we have carbamazepine, phenytoin, and lamotrigine, which will inhibit the sodium voltage channels here, so thus inhibiting depolarization. And then we have lamotrigine and ethosuximide, which will inhibit the calcium voltage gated channels and also inhibiting depolarization. So stopping the glutamate activity, essentially, or excitement, or the neuronal excitement. Then we have the benzodiazepine, which will stimulate essentially this receptor activity, this channel activity here, resulting in more GABA activity, which will inhibit the depolarization, the excitement. Tiagabine will inhibit the reuptake of GABA, resulting in more GABA activity in the synaptic cleft. Then you have the V-gabatrin, which will inhibit the GABA transaminase enzyme here, which will obviously result in more GABA being available in the synaptic cleft. Then you have another antiepileptic drug which I actually haven't introduced, which is sodium valproate, and it's quite a common drug for epilepsy, and it does actually a lot of these things which I just mentioned. So it can target the voltage channels, and it can stimulate the GABA activity. So I didn't group it into a particular class of antiepileptics. But it's important. Some important things to realize is that in pregnancy, anti-epileptics are not very safe. So consideration. So in pregnancy, we have teratogenic anti-epileptic drugs, and these include phenytoin and lamotrigine and valproate. However, it's been shown that lamotrigine is probably the most safest out of the lot, you can say, the best out of the lot for people who are pregnant. So I hope you enjoyed this video on the pharmacology of epilepsy. Thank you for watching.